Hello everyone, we are Xinyu, Xinze, Cici, and Nathan. Today we are excited to present our final project, an FPGA-based accelerator for vector and matrix operations using an autoproduct formulation. Our goal was to design a unified hardware kernel that supports dot, octal, MVVM, and 4mm operations without modifying the data path. This work was supervised by Professor Zhu Zhang. And here are our outline. So, matrix multiplication lies at the heart of scientific computing, machine learning, and transformer-based models. At this workload scale, we need hardware that provide high throughput, predictable memory behavior, and efficient data reuse. However, FPGAs face unique challenges as they have limited DSP resources, restricted on-chip memory, and significant host FPGA bandwidth bottlenecks. These constraints made it difficult to build a high-performance GEM accelerator using native formulations. This motivates us to explore computation structures that expose lots of parallelism while keeping memory access simple and regular. The autoproduct formulation of GEM addresses these constraints extremely well. Each iteration of GEM can be viewed as rank 1 autoproduct, where a column of A multiplies a row of B to produce a 4m times n matrix update. This approach has several advantages as it exposes abundant Mac-level parallelism, it enables streaming-friendly data flow, and it provides regular memory access patterns, which are ideal for pipelining and loop unrolling on FPGAs. Prior work confirms that autoproduct data paths consistently achieve high performance because of these properties. This is why we selected the autoproduct method as the foundation of our unified accelerator. Our project has three key objectives. First, we want one unified accelerator that supports 5 linear algebra operations, dot, outer, MVVM, and MM without modifying the data path at all. Second, we aim to build this accelerator using the autoproduct formulation, which naturally exposes parallelism. And third, we want predictable memory behavior, scalable performance, and flexible bitwidth support. By the end of this project, we achieved a single stateless HLS kernel that can process all operations just by adjusting the stream dimensions, making the design compact, robust, and highly general. And for the problem statement, traditional GEM can be rewritten as sum of rank 1 other products. This single formulation is powerful because, depending on the shape of A and B, it can represent all 5 operators we care about. Most importantly, each rank 1 update produces an m times n matrix of independent Mac operations, which is ideal for FPGA parallelism. This insight forms the basis of our unified kernel design. Since FPGAs cannot store large matrices on chip, we adopt a tail-level execution model. The CPU breaks the global matrices into tail of size up to max 10. For each tail, the host streams the tail dimensions and the tail data to the FPGA over syllabus. The FPGA computes the partial sum for that tail and sends it back, and the CPU accumulates partial sums. The kernel itself is completely stateless. It only computes this result for the current tile.
So here's our implementation. This is the end-to-end overview of our system. The host CPU manages tiling and packaging of the matrices. The auxiliary bus interface transports the tile payloads. Inside the FPGA itself, the kernel loads these tiles into partitioned on-chip buffers and performs the deeply pipelined vectorized outer product update. The FPGA returns the output tile, and the host performs accumulation when K is split across multiple tiles. Before optimization, our baseline kernel was fully serial. It only has 1 Mac per cycle, with no unrolling or vectorization, and there's no data reuse and also no pipelining. It was correct but extremely slow, with latency proportional to the big O of m times k times n. This baseline helped us validate functional correctness before implementation more advanced optimizations. For our optimized design, it introduces 3 major improvements. The first one is buffer partitioning, which enabling parallel reads with zero-port conflicts. The second one is column vectorization through the tile of J dimension, allowing us to process 4 or 8 output columns at a time depending on the bit width configuration due to the DSP resource limitations. The third one is pipelining the K loop with the interval of 1, letting each iteration perform one full rank 1 update per cycle. By combining all these full unrolling along the M dimension with tile J wide unrolling along the N dimension, we achieve M times tile J MAC operations every cycle. Here we compare the two designs. The baseline had 1 MAC unit, but the optimized version has between 64 and 128 active MACs depending on the bit width configurations. The baseline performs no data reuse. However, the optimized kernel broadcasts A and caches rows of B in vector registers. Finally, the baseline has no pipelining, but for the optimized version, it reaches II equals to 1 in its critical inner loop, which it refers to the K dimension. This results in up to 320 times latency reduction at the HLS level.
The next part is the evaluation. Here are our synthesis results. The optimized design used significantly more DSP, up to 87% for the 32-bit version, but in exchange, achieved dramatic latency reduction. For 4, 8, and 16-bit data, the kernel finishes as few as 11 to 41 cycles, compared to over 1,300 cycles in the baseline. Even for 32-bit, we still observe up to 193 times improvement. The clock periods remain around 8.5 to 9 nanoseconds for all the configurations. To summarize our real hardware performance results, the main takeaway is that the entire system is dominated by CPU to FPGA I/O latency. On the Z-board platform, the I/O alone accounts for about 90 to 98% of total runtime. In contrast, the FPGA compute kernel, after all our optimizations, runs in only tens of cycles, which translates to nanoseconds. This compute time becomes completely invisible compared to the millisecond scale cost of syllabus transfers. We also found that x86 hosts handle tiling and packing much faster than the ARM processor, though tiling is still only a small fraction of total time. We also tried a no-compute experiment to isolate pure I/O time by synthesizing a kernel that just reads inputs and writes 0 back. But the method turned out to be unreliable because the FPGA compute portion is so tiny that noise from HLS, non-determinism, and Linux scheduling jitter easily overwhelms it. Overall, while our optimized kernel achieved 29 to 320 times speed up theoretically, the system level throughput barely changes due to the I/O bottleneck. The implication is clear. Improving actual performance requires higher bandwidth communication such as AXI, DMA, or PCIe, and reducing host side packing overhead. Without addressing these I/O limitation, further compute optimization won't translate to observable speedups.
The next part is our project management. Our team collaborated closely across 5 weeks. Xinyu focused on the unified kernel architecture, buffering partitioning, and operator generalization. Xingze concentrated on the kernel optimization and timing closure. Cici implemented multi-bit width support and built the correctness and performance testing framework. Ethan developed the host FPGA communication infrastructure and produced documentation and figures. And here is the timeline table. This division of labor enabled us to iterate quickly and integrate our contributions smoothly. Throughout the project, we faced several challenges. First, aggressive unrolling quickly exceeded DSP resources, so we developed the tile J mechanism to balance parallelism with hardware limits. Second, bit width scaling introduced timing and routing challenges, especially in the 16-bit case. Third, some loop structures caused pipeline stalls due to memory port contention, which were resolved using temporal buffers and register vectors. Finally, the most importantly, system-level performance was dominated by host FPGA I/O latency, not compute time, an insight that shaped our performance evaluation.
The last part is the conclusion and acknowledgements. To conclude, we successfully built a unified stateless, out-of-project-based FPGA accelerator that supports 5 linear algebra operations through a single pipeline HLS kernel. The compute kernel is extremely efficient, capable of sustaining 1 rank 1 update per cycle, and it scales naturally across data width. However, system-level performance on Z-board is IO-bound, demonstrating that communication overhead can overshadow compute optimizations in FPGA systems. Overall, this project taught us valuable lessons about hardware-software co-design, tiling strategies, and HLS optimization. We would like to express our sincere gratitude to Professor Zhiru Zhang for his guidance throughout the course, and to the TAs for their continuous support, clarifications, and infrastructure assistance. Their help was instrumental to the successful completion of this accelerator system.
So next we will show a quick demo of our optimized design. This is the top design file, including the read and write function performing the communication between FPGA and CPU. This is the optimized computational kernel. And in the host, we first run some tests to check the correctness and run 2 performance tests on the medium large dataset. Also for the 4-bit design report, we can see a big improvement in the cycle performance from baseline to the alternative design. So here I will run the software on EC Linux first and see the timing report. Yeah, and here the timing report. I'll run the software on the Z-board ARM CPU next. And finally, I'll run our design on the FPGA. Here's the result. So that's the end of our presentation. Thank you.